So, what do we mean by a reaction energy profile in chemistry? Well, a reaction energy profile is a mathematical model, in this case a graph, that tells us about changes in potential energy during a chemical reaction. Before continuing with this video, you may also want to check out the cohesive chemistry video on potential energy in covalent bonds, and then continue. So what do we see in a reaction energy profile? Well, we have a graph with two axes. On the y-axis is potential energy, and on the x-axis is reaction progress. And you can think of reaction progress like a very short time scale. The first feature we see on a reaction energy profile is the total potential energy of my reactants, which is the start point for the chemical reaction. And in order for my reactants to form products, the first step of the process is always going to be breaking the covalent bonds in my reactants. And to break covalent bonds, we require an increase in the potential energy in my system. So a reaction energy profile will always move up first. At the point on this line where it begins to plateau, I have effectively broken all of the covalent bonds in my reactants, leaving me with all of my individual atoms in an unstable state. So the next step I will see in my reaction energy profile is representing all of those atoms reforming covalent bonds in order to produce my products. When forming covalent bonds, my system decreases in potential energy. So the line from this point is going to start dropping. Depending on which covalent bonds are forming, this line can drop to different levels. And in this example, the line stops dropping when all of the covalent bonds have been formed and my atoms are now in stable arrangements. So, what are the important features of this reaction energy profile? Well, the first thing is that I can see, in order for my reaction to occur, I first require an increase in potential energy in my system in order to break the bonds. And the amount of energy required to do this is called the activation energy. The second important feature in this example is that I can see that the potential energy of my products is lower than the potential energy of the reactants that I started with. And the importance of this second point is that if the potential energy in my system has decreased overall, the surroundings must have experienced an increase in energy. And when we are considering the energy in the surroundings, we are talking about thermal energy. So this decrease in potential energy in my system must mean an increase in thermal energy in the surroundings. This is what is called an exothermic reaction. Let's now change my reaction energy profile slightly to consider the other type of energy change we might see. Let's consider a different reaction in which the potential energy decreased when forming bonds stops here. In this example, the activation energy is still the height of the first increase in potential energy. But if I look at the potential energy of my products compared to the reactants, I can see that they are actually higher. So in this example, we've seen an increase in potential energy during my chemical reaction. Therefore, we must have seen a decrease in the thermal energy in the surroundings. And this is what we call an endothermic reaction. So in summary, by comparing the potential energy of my products with the potential energy of my reactants, I can work out what energy changes to expect in the surroundings. And I can identify and label these types of reactions as exothermic or endothermic.